Hi everyone, this is Guangdao Yang from Cornell University. Today I will talk about how to generate shapes by modeling them as distribution of points. In this talk, I will focus on the task of generating 3D shapes. Specifically, we want to train a model whose input is a random vector and the output is a shape. A key challenge is to choose a representation that's easy to generate and powerful enough to capture the shape. Recent works explored many representations such as voxel, point cloud, meshes, and implicit representations. We propose to think of shapes as distribution of 3D points. Points off the surface will have low probability, while points near the surface will have high probability. There are many advantages doing so. First, we can create point clouds of arbitrary resolution by sampling from the distribution. Second, we can also extract high-quality surface from the probability density field. Such representation also works for shapes with complicated topology and non-watertight shapes. Given that, shape generation can be broken down into two steps. In the first step, we will model a distribution of points that represent a shape conditional by a latent vector. In the second step, we model a distribution of shape latent vectors. After that, we can use the second model to sample latent codes for the first model to produce the shape. We explore this idea in the task of point cloud generation in ICCV paper point flow. Here, we would like to train a model that can produce a point cloud. The key challenge is how to model the distribution of points. One way to achieve that is to learn the mapping from a simple distribution, like a Gaussian, to a more complicated one. Here we use a model called continuous normalizing flow, introduced from the NeurODE paper. So specifically, a CNF models a transformation of points by moving them according to a vector field g theta. A nice property about CNF is that they are invertible, so the inverse of CNF is obtained by simply flipping the integration direction. Thanks to the fact that they are invertible, we can use the change of variable formula to compute the log likelihood of the output x. This allows us to train CNF with maximum likelihood training. Here's a visualization of a CNF transforming 3D points between a Gaussian and an airplane. We also apply CNF to model a distribution of latent code. With that, point flows can achieve state-of-the-art point cloud generation results. We can see that the point flow is able to generate diverse and realistic point clouds. But a major limitation for point flow is that it takes too long to train. Looking back at the training objective, we realize that CNF has done a lot to keep the distribution normalized. So it requires the network to be invertible. It also keeps track of the normalizing factor, which is slow to compute. But do we really need a normalized distribution to represent a shape? So here are two different unnormalized distributions. Despite different scales, we can still recognize that they capture the same shape. This suggests that a normalized distribution might be sufficient. How to best parameterize a unnormalized distribution? Outputting directly the density is confusing since the scale is unspecified. So we predict the gradient field of the density instead. There are many advantages doing so. First, it allows us to sample point clouds easily. Creating point cloud amounts to performing stochastic gradient ascent along the gradient direction. Second, it imposes minimal restriction to network architecture. We explore this idea in our ECCV paper, Learning Gradient Field for Shape Generation in a two-stage manner. In the first stage, we train the network to output the gradient field conditional on the shape latent code. In the second stage, we use the latent gain to learn the distribution of these latent codes. Inspired by noise conditional score network, our network also takes a noise level sigma as input. The output gradient field will capture different fine details of the shape depending on the sigma. During inference, we run stochastic gradient ascent while gradually annealing the noise sigma. As the noise decreases, the point cloud will reveal more and more fine details. Our method can produce clean, dense point clouds and high-quality surfaces. And our model can generate diverse and realistic shapes regardless of the initialization points. The gradient field can also represent shapes with complicated topology and point clouds from non-watertight meshes. For more information, please check out our paper and code. Finally, thanks everyone for listening. Also, thanks all my collaborators in these two papers.